Is an equation where the highest power of x is 3, and we can graph it in one of three ways. The first way is where we have a constant in front of x to the power of 3, and we're only going to start by looking at positive constants. So like our first example here, the standard graph of a cubic function is one where when x is 0, y is 0, so we go through the origin. And then here with a cubic function, notice that when I cube a positive number, I get a positive output, but when I cube a negative number, notice that I get a negative output, which means that my graph can go above and below the x-axis. So it sort of looks like this S shape, and then it goes through the origin like so. Now here, this part of the origin is what we call the point of inflection. Now here, if I look at the next example of how I'm going to graph a cubic, it's with this one here. And I've got a bracket, and I also have a constant at the end. This bracket is telling me that we have a horizontal shift, and this constant is telling me I have a vertical shift. A horizontal shift means I'm moving left or right, vertical is up or down. So with this next example, so our second one here, now with a horizontal shift, I'm going in the opposite direction. So I'm actually moving 2 units to the right, and I'm vertically shifting up by 1 unit. Now in terms of what's shifting, we're essentially taking this original cubic function and we're lifting and shifting the whole thing. The easiest way to do this is to start with the point of inflection, which is at the origin. Then we're moving 2 units to the right and then 1 unit up. So our point of inflection will be here. Now, whenever I'm graphing, not only do I need x-intercepts, I need y-intercepts. So when y is equal to 0, the y-intercept ends up being -7. So I have a graph that looks something like this. It's a bit longer than the last, but it has to go through our point of inflection and our y-intercept. Now, our last example, and it's going to be the most useful for graphing polynomials in extension 1, is this form here, which is the factored form. Now, the reason this is useful, if we think about factorizing quadratics, we typically get up to this point here. And then if we're asked to solve them, we recognize that x will be -2 and x will be 3. And what those represent for the quadratic are actually the x-intercepts. And this concept can be applied to cubics as well as other polynomials. So for this example here, what I will have is I'll have an x-intercept of -2, 1, and 2. So I'm going to have -2, 1, and 2 plotted here. My y-intercept, which is when x is equal to 0, it ends up being 5. And then I normally need to understand, is my shape, my polynomial, is it going to go up this way potentially, or is it going to go this way? And I need to figure out which is the correct way. And the way that I can do that is I can actually just test points between the intercepts. So here, for example, if I test the point, let's just say, for example, I test -1. If I substitute -1 into this equation here, then my answer ends up being 6. So it's going to go up here. So that tells me that's where my polynomial is going to go. So it's going to go all the way up here, through the intercept, through this x-intercept, through the other, and then back up again. So simply test a point, so that way you know the shape as well as the direction of your graph. Now this next part is also going to look at, well, what happens if I have a negative coefficient? And what happens is, if I think about what the negative is doing, it's basically saying take all of your y values and switch the signs around. So I end up reflecting over the y-axis. So here I end up with a graph that looks like our same shape as our y equals x cubed, but I'm actually going the other way around. Same with our other graph here. So notice that my translations are still going to be the same. I'm still moving to the right by 2 and up by 1. My point of inflection is still the same. The only difference now is that it's going in the other direction, like so. Same here, when I have this cubic function here, my intercepts are still all the same, except all I'm doing now is I'm switching the direction. So instead of going up this way, I'm actually going to go down that way. So it ends up looking something along the lines. So basically just flipping everything in the other direction. So it's important just to note when it's positive, it's sort of heading, if I look back up here, can we see that everything is sort of heading to the right? And when it's negative, everything is heading in the left direction. And that's going to be important when we're graphing our other polynomials. We also want to consider what happens when there's a root of 0. And what that means is that if I have, notice that this particular polynomial, it's in factored form. And then notice that this x isn't in a bracket. But all that means is that x equals 0 is not only a possible solution, but it's also an intercept. So x equals 0 is an intercept, as is positive 1, and as is minus 2. So then here, what I'm looking at is I have 3 intercepts, and notice that my cubic function, that with a cubic, the degree is 3. And notice in this case, I have 3 x-intercepts. And we're going to touch on what that looks like and in the other 2 examples as well. So again, what I'm going to do is I need to first find my y-intercept. So when x is 0, y is 0. So I know that that's going to be that point there. I would then test a point. So let's just say I'm testing maybe -1. If I substitute -1 into this equation here, what I end up with is an output of 2. So what that means is I know that my graph is going to go up this way and down and then back up again. So that's helping me determine the shape of my graph. So it will look something like so. You can also apply the same idea to how, for example, knowing how deep do I make this. Again, you can substitute in a point. So here, for example, just circle this down. For example, if I substituted in a half into that equation, I end up with -0.625. So that's how I know that it's not as large of a dip as the first part of that function. Now, the next one that I'm looking at is notice that I have only 2 brackets, but one of those brackets is a squared. So I want you to think about this squared is what we call a double root. And a double root means that I still have, I have 3 possible solutions, but 2 of those solutions are actually the same. So 2 of them are going to be +1 and the other one is going to be 3. So I'm going to go through 1 and I'm going to go through 3. Now a double root, the shape of that, it actually looks similar to that. Think of like a quadratic where the highest power is 2. And notice that when I have a quadratic, that I have a U shape. I have a vertex, if I have something like here. So that double root is actually going to reflect that. I'm actually going to have a vertex at that particular intercept. So here, what it will look like is, again, I'm going to test a point between 1 and 3. So let's just say I'm going to test 2, and it ends up being -1. So here, what happens is that I know my graph is going to go through the point 2 - 1 by substituting that in. And I know that I'm going to get a double root that looks like a turning point or a vertex. So it goes through the y-intercept. It touches this point 1 here, drops down, and then goes back through 3 again. My last one is, notice I have another double root, and I have also x equals 0, and then I also have it in the negative direction. So here what I'm looking at is that I have 2 intercepts. I have one at 0, and then I have another one at -1. However, I know that the intercept at -1 is going to resemble that of a vertex because it's going to be a double root. I just need to know if the vertex is going to be facing this way, or this way. So to do so, I'm going to test a point. So for example, if I test a point between these 2 here, or another way that I can tell is that, notice I've got a negative coefficient, and notice that with negative coefficients, I'm always heading towards the left. So I know that my graph is going to be in this direction here. So I'm going to go through minus 1, but remember I have a double root, so it sort of looks like a turning point here, and then I go through the origin again. So I can either test a point or I can use my understanding of negatives to know the direction that it goes in. Finally, if I want to look at applying this to another polynomial, so here I've got this polynomial here, and I want to be able to write it as a product of its factors. So basically, I want to write it in factored form. So here, for the first part, so P of x, notice that x is a common factor, so I'm going to factor that out. X squared is a common factor, so I have x squared plus 2x minus 3. I can then factorize this quadratic here even further. So here I can actually factorize it as x squared outside of x plus 3, x minus 1. So that's part A done. Now part B, it says sketch the graph. So whenever I'm sketching, I will have my x-intercepts. I also need my y-intercept, which is when x is equal to 0. So when y is equal to 0, plus 3 and 0 minus 1, my y-intercept is 0. When I think about my x-intercepts, notice that I can gather that from the factored form. So here my x-intercepts, when x equals 0, which is also a double root, because notice that I have the squared here. Here I also have a root of minus 3 and 1. Now here, I'm going to have up my Cartesian plane. Now, I also want to understand is when I go to label my intercepts, I'm going to go through 0, I'm going to go through minus 3, and I'm going to go through 1. Now, I want to understand what direction I'm going in. So I want to know is my graph going to go up like this, or is it going to go sort of like this? And I need to figure out what direction. So to do so, I can actually test points. So what I'm going to do is that, for example, I'm going to test when x is equal to minus 2, my answer is going to be minus 12. So notice that when x here is minus 2, I have something down here at minus 12. So I know that my graph is going to go down here and then back up here. I also want to know how deep this part here is going to be. So I'm going to test a half. And when I test a half, I get an answer of negative 0.438. So it's somewhere probably around here. So when I go to connect everything up, first I need to go through all of the intercepts. I need to make sure my graph hits these points, and I need to remember that this is a double root, so it will look like a turning point or a vertex. So here I'm going to start drawing my graph. It goes through this. I also remember that the y-intercept is 0, so it would already go through that point here, and then it goes back up again. And then I always like to label my function f of x. Or if I have an odd degree of a polynomial, such as a cubic, it's going to look like this far right-hand column here. So here I have a positive leading coefficient, so I could have y equals x cubed. Notice that as x is approaching infinity, y is approaching infinity. So that means as x is getting bigger, y is getting bigger. So that's why my graph is heading towards the top right-hand side. And as x is approaching negative infinity, y is also approaching negative infinity. Now this flips when I have a negative leading coefficient, such as y equals minus x cubed. So here, that's why the direction of my graph is to the top left. And in this quadrant here, it's to the bottom, it's heading towards the bottom right. However, if we have something like our last example where I had the highest degree, which is 4, that's an even degree, I have something like this column here. And notice that both ends of the graph are heading in the same direction. So on the right, as x is approaching infinity, so is y. But here, as negative x is approaching infinity, y is also approaching infinity. Because if I think about squaring or finding to the power 4 of a negative number, my answer will always be positive. So that's why it's heading up towards this direction. If I had a negative leading coefficient, I have something like this, which is like concave down, and here's x approaches infinity, y is approaching negative infinity. So here, an odd degree, I'm heading in two different directions, but here for an even degree, I'm heading in the same direction.